3 o'clock, so let's get started again. Everyone have a good Memorial Day weekend. Nice and relaxing. Now you get to come back and do some more algorithmic stuff too. Woo! So, as you all know, assignment 2 is due today at midnight, so any questions about assignment 2? Everything pretty straightforward. Yeah, it should be pretty straightforward. I've also posted assignment 3. So some of the parts that you'll be doing in there, so it's a little more work. It's worth 15 points now instead of 10 for the first 2 assignments. So some of the cool things you'll be doing are, we've talked about the 8x8 queens problem where you try to place 8 queens on a chessboard, and we've found out that you can do that via a backtracking and constraint satisfaction strategy. So just trying to, we just place a queen and then we find everywhere we can possibly place the queen and then try the first one and then recursively call ourselves on that. So here we're actually going to do a different kind of problem, Sudoku. So how many of you have not played Sudoku? Okay, so everyone's done Sudoku. So what you'll be given is an incomplete board that looks like this, and then you'll basically solve the Sudoku puzzle via multiple steps. So I have some figures which show you how validation of a Sudoku board is done. So basically, the way it works is you make sure that every single row and every single column has all the numbers 1 through 9 exactly one time. So like the second column here is 4, 3, 9, 8, 5, 1, 6, 7, 2. So every number 1 through 9 is in there. There's no duplicates, none missing. And it's also every 3x3 square that, so like the first 3 rows and columns, so like the upper 3x3 square, the next, and all the other 3x3 squares, each of those has the same property, that every single integer 1 through 9 is in there exactly one time. And so that's what's called a Sudoku puzzle. So what you'll be given is an incomplete puzzle, and then you'll just be filling in the integers that will go there. And luckily, I'll make sure that there's only one unique puzzle that you could possibly get out of it. So it turns out that if I give you a completely empty grid, then you can just, there are many possible solutions, right? So there's actually a really cool paper that might be a cool project idea, which is, if I have it on here, is at this archive link, which says that you must be given at least 17 squares to guarantee a unique puzzle. And so it might be really cool to figure out how they were able to verify all possible Sudoku puzzles, because as you may know, there are 9 choices for every single placement in the grid, and since it's 9 by 9, it's 81 squares, so 9 to the 81 is a very huge number. So they can't possibly verify all of them, so it might be really cool to figure out how did they actually verify that. That there are Sudoku puzzles with 16 given squares that have multiple solutions, but every single one with 17 as a unique one. But anyway, so the first part you'll be doing is you'll be given a complete grid, so 81 integers, and so what you'll need to figure out is whether that grid is actually a Sudoku grid, like it's a valid Sudoku grid, because I can give you just 81 9s in a row, and that's obviously not good. So you'll just need to verify whether it's a valid puzzle. The next part is you'll actually figure out what are the constraints. So what constraints do we need to satisfy, that kind of thing. So you need to go back and figure out what is a constraint satisfaction problem, what are the things I need to fill in, and what do those correspond to with Sudoku. And then the final part, which is the biggest one, is actually solving it. So given an incomplete puzzle, and then I specify a format, but you'll use your checker to figure out whether you have a valid Sudoku grid. Okay? And then I have some format and a sample input. The next part is one that's you won't do as much on, but it's kind of the same flavor. So a magic square is basically an n by n grid where each of the numbers between 1 through n squared is used exactly once. And another really cool thing which makes this a magic square is that every single row every single column, and each of the two main diagonals add up to the exact same number. Okay? So here, this row adds to 15, 15, 15, 15, 15, 15, 15, 15. So this magic square's value is 15. So this is just one example, but you could be given, say, a 4 by 4 square or a 5 by 5 square, right? And so what you'll be given is a list of integers just to validate whether it's a magic square or not. Okay, pretty simple. And also you'll do a constraint satisfaction approach too. All right. And then one of the last parts is a generalized n queens problem. So we covered 8 by 8 queens, trying to place 8 queens on the board, but what I'm asking you is I'm going to give you an integer n, and I want you to output a board of size n by n with the placement of the queens. So we know how to do 8 by 8, but I want you to be able to handle any value of n. Okay? So you'll just do the same approach for backtracking and constraint satisfaction, but I want you to be able to generalize it instead of just doing a solid 8 by 8. Okay? And so this part doesn't have any constraint satisfaction or anything. It's just the programming part. And that's assignment 3, and it's due whatever date the 5th is. I think that's a Tuesday. No, it is I think it's a Sunday. Yes, it's Sunday. Okay. So any questions on assignment 3? Yeah, I think that's fair because I want to leave a nice chunk of time at the very end, like 2 weeks or so, for you to finish up your project, because that's the most important. I think the most important part of the class. So I don't want you to have a whole bunch of assignments at the end, and I know if you're taking other classes, then they're going to fill you up with assignments at the end, so I just want you to have only one thing to worry about at the end. So, any other questions? Okay. So we have a topic today that we're going to start brand new, which is divide and conquer. So after this set of lecture slides, we're going to actually finish everything that the previous offering of the course already did. So this is the very last thing that they covered. So after this, we're going to get into the really exciting things that I really like, that are really interesting and have a bunch of applications, a lot of cool problems there. So actually, this is really cool too, but the stuff that I'm interested in and is even more non-trivial is stuff after this. But let's get started with this. So what do you think divide and conquer actually means?
Is it similar to like how merge sort?
Exactly, yeah, it's exactly like merge sort. So what you're doing is you're given a particular problem, you split it up, and what you do with those parts is that you recursively call yourself until some base case happens. Then what you do is, once you're done doing all the recursion, combine the results. So how merge sort works is you take an unsorted list of n integers or n anythings, you recursively call yourself on 2 pieces, the first and second half, and then once you're done recursively calling, you merge the 2 parts together, these 2 sorted n over 2 size lists. Okay? And how you do that is you iterate through each of the lists and add each of the elements in order, depending on what they are in each of the sublists. And then obviously output the new solution after doing all the recursion. All right, so the idea in general here is make simpler instances of problems. So make a smaller call on yourself that are easier to solve instead of just the general thing, and then combine the results at the end. So just split the problem up in general. All right, so we'll be talking about, I believe, 3 problems. So the first one is called peak finding. So what we're given is a list of integers, n integers. And so what our goal is to find what is called a peak in this list. And what a peak is either at the ends of the list, if they're greater than or equal to the elements before, or some element in the middle that's greater than or equal to its neighbors. So if you have, say, a list that has in the middle 2, 4, 3. 4 is at least 2 and 3, so 4 would be a peak. So we can actually, it's actually a simple exercise to verify that every single array has a peak, at least one peak. Okay? So it's either going to be in the middle or it's going to be at the ends. But the question is, what is the runtime of actually finding such a peak? All right, so if it's at the beginning or the end, then it is a peak if it's at least the one neighbor associated, because there's no element on the other side. So like there's no A0 here or AN+1. So the idea is, how would you approach this normally? Well, what's a really simple...
Start at the beginning and compare every number as you go.
Right. So just do a brute force strategy, because we can just iterate through the entire list, right? We start at the first element and then check all possible neighbors, which are the either one or two neighbors it has. Then if it's greater than or equal to that particular neighbor, then output that solution. Then otherwise, then we just keep moving through the list until we find such an element. Okay? It's just a brute force idea. So we compare each of the indices with the associated neighbors, and one of them is if it's at the ends. If it's a peak, then output that particular index, and otherwise keep moving. So what's the time complexity of this? Yeah, a big O event. Yeah, pretty simple. Because we may, through an adversarial argument, we might be able to go all the way through to the very last element of the list before we find a peak. So we may have to traverse the entire list there. Okay? Can we do better? So it turns out, yeah, we can. So we're not actually going to just improve the constant hidden in the O notation. We're going to actually improve this asymptotically, which is actually really cool. So let's just say that we have an index I, right? And if it's a peak, then we can return it, right? Then what if it wasn't a peak? Then that means that if it's not a peak, then it's not greater than or equal to both its neighbors. So that means there's one neighbor that's strictly larger. Actually, both neighbors are strictly larger, right? Right. So it's locally increasing on either side, right? The definition of peak says that you need to be at least as large as both of your neighbors. So if it's not a peak, then it's either strictly less than both its neighbors, or it's less than it's greater than or equal to one of its neighbors and less than one of the other neighbors. So you know it's increasing on one of the sides, right? It can't increase forever, right? So only two things can happen. It either increases all the way to the end. Is there a peak there? Yeah, because I said that if it's at the very end of the array and it's larger than the second to last element, then that means it's a peak. But what's the other case? It goes up and up and up, and then it comes back down. Did I just find the peak? Yeah, it just went up and then went down. So there's some index that's larger than or equal to both of its neighbors, right? Did I need to look at that first half? No. I didn't even have to sort the list, right? So there must be a peak somewhere on that increasing side. So basically, since we want any peak, it doesn't matter what peak we pick, right? We can throw the side that's not locally increasing, right? So what we do is something like binary search. We don't have a sorted list here, but we can still do a binary search kind of idea here. We look at the middle element. Either it's a peak or it's not, right? If it's a peak, then we can just return it. If it's not, then we survey the two elements next to it. Either it's strictly less than both of them, or strictly less than one of the two sides, because those are the only two possibilities, right? So we just go if it's strictly less than both of them, then just pick one of the sides. If it's strictly less than one, go to that way. So if it's strictly less than, say, the first half of the list, then recursively call on the first half of the list. Okay? And then we recurse until we find such an element, because there always will be a peak, no matter what. So just as a pseudocode kind of thing. So we're given this list A with starting index I and ending index j. So at the very start, I'm going to call this find peak with the array of integers that I have, with starting index 1 and ending index n, because I want to survey the whole list at the start. But this is just in general from index I to index j. So I want to find the middle element, so it's just the floor of the starting plus the ending index divided by 2, it's just the average, and then take the floor. So we have one case, either it's, so this case basically handles if it's at the beginning of the list. So if it's at the beginning of the list and its value is greater than the second element, then we must return that peak, because that's the definition of a peak at the starting end. If it's at the very end and it's greater than the second to last element, then we must return that. So those are just the two edge cases there, literally edge cases. But otherwise, so in those two first if statements, I actually didn't I didn't actually use the value of the middle element here. So, but now I have the case where the middle element's not at the end, right? So what I'm doing is I'm going to make sure that if this middle element is greater than both of its neighbors, then we obviously have a peak, so we must return that one. But otherwise, if the larger element is on the first half of the list, so it's the element right before, then we basically go up until the middle element minus 1. And then otherwise, the only other possibility here is that the second half of the list has the first element being greater than the middle element, in which case we call on the second half of the list. Okay? And so now let's look at the runtime. So effectively, we remove half of the array every single time, right? And if we look at how the code works, what are we doing here? We're doing a couple lookups and then checking of a particular value, right? So how much work am I actually doing here in like those if statements at the beginning? I'm doing constant time, right? So every single level of the recursion, I'm doing constant time amount of work. And I remove half of the list every single time. So how many possible recursions could I do? Well, I'm doing divide by 2, divide by 2, divide by 2, divide by 2. Does that sound familiar? Sounds like binary search, right? What's the complexity of binary search? Binary search is log n, right? It's because I remove half the list every single time. So the complexity of this is log n. So there's a constant amount of time needed to check if an element is a peak at all. Then we have log n recursions. Log n recursions, so basically log n recursions times constant amount of time per recursion. That's a logarithmic time algorithm. Okay? Isn't that pretty slick? N versus log n. That's actually quite a big difference. Even though we sometimes encounter algorithms that are like 2 to the n, like we did with like generalized n queens, right? Because we may have an exponential number. So it may seem like n is not much different from log n, but it actually is a huge difference here because it's exponentially less. And we'll actually see this in the next problem. So are there any questions about how we were able to look at this? So basically, we were able to divide the problem up and conquer on that one particular problem. So that's actually a different flavor than merge sort works, because what merge sort did is it had multiple solutions, right? And it combined those multiple solutions. But here we only have one solution to look at a given time. So there are different flavors of divide and conquers. Some that only have one recursive call, and then some that have many. Okay? Any questions about this?
So recursion is, the runtime for recursion is usually big O log n.
Uh,
I mean, is it long?
Well, when you get just log n, it's basically when you divide the problem up into 1/2 of its original size and only work on that original half.
Okay.
Yeah, because it's
Can we work on both?
yeah.
Which still be log n?
If you work on two pieces, like how merge sort works,
Yeah.
it really depends on how much time you spend combining the solution at the end. That's where the real magic happens, and that is all about when we covered the master method last time. That the way that works is you look at how much time is done per recursion and how much work times the amount of work done at each level of recursion. So the amount of time you actually spend to combine the solutions really does matter there. So it depends on the problem you're looking at, but yeah. So any other questions about this? Okay. So another one that's actually really useful is closest pair of points. So this is useful in computational geometry and many other applications where what you're given is some set of points, either in just on one line or 2D or 3D at any dimensions, right? And what you want to do is you want to find the pair of points, so 2 points, that have the smallest distance between them. So anyone not know how to compute distance between points, like in Euclidean space? So like like in 2D, it's if you have 2 points, x1, y1, and x2, y2, you take the difference of the x's squared plus the difference of the y's squared, and then do the square root over the entire thing, right? So that's just the Euclidean distance in general. So what we want to do is we want to find the pair of points such that they have the smallest distance between them. Okay? The closest pair of points. So I say that there's an obvious n squared algorithm. So what's that algorithm? There's a flavor of how I'm presenting these. You start with brute force and then we do divide and conquer. So
2 for loops.
yeah, just do 2 for loops, right? Look over every pair of points. So for I in the list of points, for j in the list of points, and make sure I is not equal to j here. But calculate the distance between I and j, and then you see if it's the minimum so far. If it's less than the current minimum, then you store that pair. Okay? So there's an obvious n squared algorithm. Just loop through each of the possible pairs. And you can actually do better on the constant here. You can just say, if you have some order, like the points are listed 1 through n, then you do a for loop for I in the list. But you don't want to do pairs that you've seen before, so you say for j in I plus 1 to n. So you don't do pairs twice, right? Because you may do I is equal to 1, j is equal to n, and also do I is equal to n, j is equal to 1. Because the distance between the nth and first point is the same as the distance between the first and the nth point. It doesn't matter what order you see them. So you can improve the constant here, but you can't do a whole lot about reducing the exponent runtime. So let's just see if we can actually do better than this. So iterate over all the pairs of points, compute the distance, and keep the pair that has the minimum distance so far. Can we do better? And we can actually achieve n log n. So this is basically reducing n to log n here. And we're going to actually do a code demo here, and we'll be able to see how much of a difference that actually makes here. And it's a huge difference. I couldn't believe how much difference that made. But anyway, so in one dimension we can achieve this. A project idea is I think it is listed on the list of projects, is can we actually keep n log n for higher dimensions? Because n squared definitely will work for any amount of dimensions, as long as you can keep constant amount of time per pair, right? Because you can just do that brute force method. But that's just a project idea. All right, so what we're going to do is I'm going to leave 2 dimensions and up to the project, and let's just work on 1 dimension here. So 1 dimension, that's just points on the line, right? It's just a assortment of points on the real line. And what we can do is we can sort the points in n log n time, right? Just pick your favorite n log n sorting method, like merge sort, for example. And then let's look at the cases. If there's 1 point, then it actually shouldn't say return 0, because what is the distance between any point and any other point in the set of 1 point? It doesn't really make sense, right? So we can just say like infinity, right? Because there's not even 2 points in there. If there are 2 points, then we can return a distance, right? Because the shortest distance between any 2 points within a set of 2 points are the 2 points itself. There are no other points to choose. Otherwise, there are more than 3, right? So what we're going to do is we're going to randomly pick some value x in the list. Just pick any one you want. And what we're going to do is we're going to put all of the elements that are smaller than x into one set, and everything that's at least as large as x in another set. Right? So we're partitioning the list into 2 sets. Does that sound like a familiar algorithm? Something about pick something and move everything that's less than it into one part of the list and everything that's greater into another part. Does that sound familiar? Starts with a Q. Quick sort? Yeah, it sounds like quick sort, right? It's the same idea as quick sort. Just move everything into one half of the list and things into a separate half of the list, and then recursively call on each. Recursively call ourselves on those 2 parts until we get to one of those 2 base cases. And let's just say that the result of that recursion is D1 and D2. So the shortest distance among any 2 points in S1 is D1, so D1's some number. S2 is the smallest distance between any 2 points in them is D2. So we handled each of the 2 parts, right? So what are the only possibilities that cannot be the minimum of D1 and D2? Could there be a smaller distance? So I basically partitioned it into 2 parts. So where could a smaller distance live? Well, it can't live all in each of the 2 parts, right? Where else could it be? 1 in each, right? So there could possibly be many of those distances, right? Let's see what happens. There could be a smaller distance. So how do we merge them together? So let's just say that D1 corresponds to element P1 and P2. So P1 and P2 are entirely on one side, and Q1 and Q2 are entirely on another side. Okay. So we know that one of these 2 is the smallest, or there's a pair that lives across this element x that I chose that has a smaller distance, right? Those are the only 2 possibilities. So let's just say delta is the minimum of D1 and D2, right? So that means that it's the smallest distance, not counting the ones that go across x, right? Well, here's the key here. So if there is a smaller distance across x, this separator I made, then let's just say R1 and R2 are those possibilities. Then they have to be within delta of x. They can't be any farther apart than this. Why is that true? Well, let's see. So let's just say x is right here and delta is out here. And let's just say R1 and R2 have a distance that's larger than delta away, right? Well, that means that they must have had a smaller distance than any other one, right? Because we would have caught it in this P1, P2, and Q1 and Q2, but we didn't. So they have to be within delta of this middle figure, right? And in one dimension, R1 must be the largest value, right? Because if it wasn't the largest value, like if there was someone that's closer to x, then there must have been a shorter distance. right? So R1 must be the largest value in S1, and S2 must be, it actually should say the least, the closest one to X in S2, right? And by definition, there must be at most 1 point, because if there was more than 1 point here, then since this area is delta and it's one dimension, we would have caught it already. Because if there were 2 points in this x to delta interval, it has a distance less than delta, which means we would have caught it in doing the recursion, because they're both on one side. They're not on two sides. So there must be at most 1 point on either side. Okay? Anyone confused by that? Okay. So there may be 0, but there must be at most 1 point on either side. So now let's do a pseudocode version here. So I'm given this set of points S, and I want to find the closest pair. So I'm going to return the distance, which is the closest pair. I'm actually not going to return the pair here. I'm going to return the distance itself. So if there's only 1 point here, that actually is a bug. It should say like infinity or something like that, because there aren't any other points to choose from. If there's 2, return the absolute value of the difference between those 2 values, because that's the calculation of a distance in one dimension, right? Because it's just some real number minus a real number, and it's the absolute value of their difference is the distance, the actual distance between them. Otherwise, we must have at least 3 elements here. So a good candidate is median. Why should I choose the median here? Well, it's like in quicksort, right? I might choose a bad pivot. What if I chose a bad pivot? Like say, if I chose it happened to be the very largest element. So n minus 1 elements on one side and 1 element on one side. So that means I'm going to recursively call on n minus 1. Then I may recursively call on n minus 2. ... So that would give us an n squared algorithm. But why would I choose the median here? What is the median defined as?
The center of the set.
Right, so it's basically about n over 2 elements on one side, n over 2 over here. So I'm dividing the list into 2 parts. Does that sound familiar? Yeah. So that's why I choose the median, so I can get a good recurrence. I can divide the list into 2 good chunks, so that I don't get too long of a time running algorithm here. So I'm going to divide S into those 2 parts. So S1 has everything below this value M, and S2 has everything above value M. I'm going to recursively call on myself with S1 and get D1 and D2 with S2. So D12, I'm going to denote the minimum distance across M. So I'm going to this basically hides checking how many elements are within delta of X on, so not X, M here. So it does all those checks there, but it's a constant amount of time there, so I'm not too worried about it here. But basically, it's the minimum distance across M. So if there are 2 points across M, then it has some distance, because I said that there's at most 1 point on either side, so there can only be 1 distance or 0 here. And so basically, I have 3 distances. I want the minimum, so I just return the minimum of all 3 of them, right? Because it could be D1, it could be D2, or it could be D12, depending on the circumstances, okay? So any questions about how this algorithm works? So we're going to code this up. All right. So what I have here, so I have a code module like we've seen numerous times here. So I have a main function which will time each of the 2 functions that I'm going to make. This time func calls timer on the timeit module and will run for 3 times and then output the average amount of time it took to do those 3 times. And then run func just runs the func that's given to it on this random list. So what is this random list? It's just, I'm calling random.uniform, so it's a uniform distribution over, it happens to be -1,000 to 1,000 here, so it returns a real number between -1,000 and 1,000, and I generate endpoints in there. So basically I'm going to have a 1,000 element list between -1,000 and 1,000, and it's going to be totally random, this list. So what I'm going to do here is I'm going to implement brute force and this divide and conquer strategy. All right. Let's see. So if there were no elements in the list, then I can just return infinity. So we haven't covered this yet, but there is a way to do sort of infinity on Python. And that's what is called sys.maxin. So, not maxin, that's Python 2, max size. So I'm going to keep this minimum distance, and I'm going to set it to be sys.maxsize. All right, so what was the idea behind brute force?
That you check every element.
Yeah, so I basically go through the entire list and also have another loop that goes through the list also. And then I do the distance on that element, on those two elements. So for I in range len of L, so I do need the index I here, so I can't just say for like lm in L or something. I actually do need the index because we talked about this optimization where I only need to do half of the work that I've done before. So instead of starting from the beginning on J, instead of having to worry about for some pair, I'm going to do it again in reversed order. So what I'm going to do is I'm going to prevent that from happening. So I'm going to go from I plus 1 up to len of L instead. Okay? So instead of worrying about having to do that case. So this will actually speed up our algorithm by twice as much, which is nice, but divide and conquer will beat it. So if we've seen a new INJ that has a smaller pair, a smaller distance, then I want to update min distance, right? So I can just say min distance is equal to the minimum of itself and the distance between this IJ pair, right? So the minimum of what it is so far. And so how do we find, so the elements I'm looking at are L of I and L of J, right? So how do I find the distance between L of I and L of J?
Just L of J minus L.
Yeah, absolute value, yes. So absolute value of L of I minus L of J. Good. And then at the end, I want to return min distance. It actually doesn't matter here because I'm just going to run the function. I'm not going to use it. But this is just basically how you would do it. All right. So now let's get to, actually I'm just going to run this by itself and not do the time func for this one yet. So let's see. So Python 3 1D points. All right. So for an 1,000 element list, it took about a quarter second average over 3 times. So let's see. What was the runtime of the brute force algorithm? Asymptotically.
Was it n squared?
Yes, n squared. So 1,000 elements took about a quarter second. So how long do you think 2,000 elements would take?
Half a second.
Well, it would take n squared, so I increased it by 2. So 2 squared times as long, so 4 times. So a little over a second here. So let's see. So about a second. So obviously it's not going to be exact every single time, but it's confirming our suspicion. All right. So what we're going to do now is we're going to implement divide and conquer. So we had those 2 base cases, either we had one element or we had two elements, right? So if the length of our list is 1, then we can just return what the min distance was here. So just return sys.max size again. Return sys.max size. Otherwise, it could have 2 elements, right? I'm just going to indent like this. So it returns 2 elements. So what should I do here? Regular distance. Do we have a function that computes regular distance already? Yeah, brute force does it. Yeah. I'm not concerned here because it's only 2 elements, right? It's not a really huge list, like 2,000 elements. So it doesn't matter if I call brute force here because it only has 2 elements. But I better not call brute force inside this else clause because it could be a really large list again. All right, so how do we find the median of a list? What's one easy way? I actually mailed on the Google group about this. Well, what's that? Well, it's unsorted, right? Well, one thing you can do is what you did, but sort the list first and pick the middle element. And that's actually how the Python standard library does this. So that's an n log n algorithm. And it turns out there is a linear time algorithm for getting just the median. And it's actually really cool. It's one of the project ideas. So if you want to do that, that's cool. But I'm going to stick with how Python does it. So there is a module called statistics, which is actually really cool. So it does a whole bunch of things like the average of a list, mode of a list, a whole bunch of things. But it also does median. So what I'm going to do is I'm going to let my m here, which is that element that I'm going to split my list into 2 parts. It's going to be the median of our list because, as we know, median is a good separator of a list into 2 parts. So the way you call it is statistics.median of our list. And what statistics.median is, what it does is it sorts the list, then finds the middle element. So just a typical median algorithm. All right. So what I need now are the 2 sublists, right? So everything that's less than m on one side, everything that's greater than m on the other side. So I want my S1 to be the elements that are less than m. So I'm going to write my entire list into one line. So this this generator expression, list comprehension expression. So for every value in L, if the value is less than or equal to m. I can actually do less than here, but it doesn't really matter. So I want every single value in the list if the value is less than m. So this will be everything on the left side of m. And then S2 is basically the same thing if val is at least m. So I just partitioned my list into 2 parts. Okay? Cool. Now what do I do with these 2 sublists? I partitioned my list into 2 parts. What do I normally do with 2 partitions? How did we do that with merge sort? We partitioned the list into 2 parts. What did we do with those? Oh, before we merge them. Recursively call, yeah. So what we're going to do is we're going to recursively call ourselves, right? So we're going to call divide and conquer of S1 and divide and conquer of S2. And so what these are going to do is it's going to look at the points on the S1 side and the S2 side and return the smallest distance of each side. Okay? So this is going to return, say, D1, a distance D1, and this is going to return a distance D2. All right. And so now we have that business where there could be a distance in between, across the median, right? So what we're going to do is we're going to let delta, which is the minimum of D1 and D2, where we looked at how delta, if there's any element within delta of m, then there could only be one on each side, right? So I'm going to let delta be the minimum of D1 and D2. So now I want to check, I actually don't need to here, but I want to look at all the elements that are within delta of the median. So I'm just going to call this others. So basically another list expression, val for val in L. If now I want to make sure that the distance between every single val I look at and the median is less than, and the median is less than delta. So this if statement is going to be what? And here's a hint. So that the distance between every single value I'm looking at and the median is less than delta. So if absolute value of value minus the median is less than or equal to delta. Okay? So as we talked about, this could have 0 points, 1 point, or 2 points. Do we have a method to do this already? We actually have two, right? So we can either call divide and conquer or brute force. I'll call brute force. So D12, which I talked about, is the distance across the median, is going to be calling brute force on others. So there can only be 0, 1, or 2 in there. And now I have 3 distances, and I want the minimum one. Right? So I just return the minimum of D1, D2, and D12. Okay? Any questions on how we were able to implement that? Cool. So right before we take a break, let's run this. And now I want to uncomment this. Isn't that shocking? Let's increase it a little. Let's increase it to 3,000. So brute force is going to take a little bit. Isn't that shocking? I couldn't believe it the first time I saw it, but isn't that pretty awesome? So just a quick analysis of how you were able to split the problem into 2 parts, recursively call on each one, and not spend a lot of time combining the solution, you can get a huge speed up here. Just by analyzing the problem just a little bit, we were able to get a dramatic speed up. Isn't that awesome? Any questions about how we were able to do that? All right, let's take a break. All right, let's start up again. So are there any questions before we get back into the material? Okay, so we've been covering multiple divide and conquer problems. So we looked at closest pair of points as well as finding a peak in an array. So we're now going to cover 2 more. So how many of you have heard of the Towers of Hanoi problem? Quite a few people have. So it's quite a famous problem, both in algorithmics and historically. So if you want to look at the history, it's actually really fascinating stuff, but we're going to look at it from an algorithmic perspective. So what you're given is 3 pegs, right? So there are 3 pegs that are standing up and n disk on one of the pegs. And they're all different size. So there are no 2 pegs with the same size. No disk with the same size. And our goal basically is to move all of the disks onto one of the other pegs. One of the other ones, it doesn't matter which. And so we can't just directly move them because we're subject to the following restrictions. We can only move 1 disk at a time. And we cannot place a larger disk on top of a smaller disk. So at the beginning, it's basically looking like a pyramid, right? So the smallest disk is on top, then the next largest, then the next largest, all the way to the bottom. The other 2 pegs are empty. And we want to be able to move this entire stack of disks onto one of the other 2 pegs. And so that basically at the end, since they're all different size, we're going to have the same arrangement, but on one of the other pegs. And the disks are all on one peg, the smallest on top, biggest on the bottom. And can we do this? Yeah, it turns out we can. So this is just a graphical representation, a crude representation, but basically we have the smallest disk on top, largest disk on the bottom, and I want to move these onto one of the other pegs. So what's an easy way to think about this? Well, we can just say, well, what if I was able to move the bottom n-1 disks onto the other one? Let's just say I had a magic way of doing this. So let's just say we were able to magically move, actually the top n-1. So let's say we're able to move all n-1 pegs, n-1 disks onto another peg. And so now I just want to combine the solution, right? So I want to be able to move these n-1 disks on top of the biggest disk on one of the other two pegs. So I'm just going to, let's just say I want to move it onto the middle one. And so now I'm going to assume I have a way of moving n-1 disks again to move these n-1 disks back onto the top of the largest disk. So like that. So we went from this, so I assume I know how to move n-1 disks from any peg to any other peg. So let's just say I had a magic method that went from the first to the third peg, like this. Then I certainly know how to move one peg, right? That's easy. So I know how to move one peg. Then I consult this magic method again to move from the third peg to the second peg, which is like this. And now we have accomplished our goal. So the magic here is in the recursion here. All right, so the algorithm idea is we have a magic method to move n-1 disks from one peg to another. And how do we do the last disk? We move the biggest disk onto the one other peg that is unoccupied currently, and then use our magic method to move the n-1 back to on top of the largest disk. So we code this up. So the way that this is structured is we have this list of pegs. So you can think of this like a sorted list of integers, for example, but you can just, it's not really important here, but start and dest are the important parts. So start is going to be, say, 1 through 3, and dest is 1 through 3. So start is, I'm going to move the top peg onto the dest peg. The disk on top of the start peg onto the dest peg. So if there's only one peg to move, then we just move it, right? Because I don't have to worry about any smaller, larger condition here. So I can just move. So I'm just assuming here that I have a move method, which could be like printing to the screen, moving this peg to this disk to this peg or something like that. But I'm not concerned with what it does, but I'm just assuming I have that method. But otherwise, I must have more than one disk to work with, right? So I'm just basically going to recursively call myself with n-1 pegs. So I have another method, say all except last, which intuitively says that I'm going to pick every single disk in this list except for the very last one, right? So it's basically saying the top n-1 disks at the start. And then I'm going to move them all to the middle peg, or the last peg, it doesn't matter which here. But I'm going to, let's just say I had a magic method to do that. Then I want to move that last peg that was on the last disk on the first peg as before, and I want to move it to where I want to move, right? So I'm moving where I want to move, and then I'm recursively calling myself again to move those n-1 disks on the middle peg to my destination on top of this largest peg. Okay? So does anyone see how that was able to work? So I'm dividing the problem up by saying I'm going to work on the first n-1 pieces, right? Sorry, I'm going to recursively call myself on the n-1 pieces. I have a solution for that, let's say. Then I have this last piece. How am I going to work those n-1 onto the very last one? So how am I going to combine my solution together? Okay? So what we were able to do here is, suppose we were able to move n minus 1 disks at once. Then we have a way of moving that very last disk onto the place we want to go, and then moving the n minus 1 again. Okay? So any questions on how we were able to do that? Okay, so let's just look at the runtime. So I'm just assuming here that I can move one disk onto another peg in one step. I'm counting this as steps now, not like seconds or anything, but the time to move one peg. So we make 2 recursive calls of size n minus 1, right? Because I'm moving n minus 1 things twice in the recursive call. So basically our runtime now is I'm doing 2 recursive calls on the size of n minus 1, plus the time to merge them. It actually should say O of 1 here because, actually no, it's not. It actually is exactly 1 here because I'm only moving that last peg one time. And the second one of the t minus 1s does the second n minus 1 moves. So what do you think this runtime is? Well, let's see. I doubled the number of smaller instances, but only decreased the size of the list by 1. So if I went down to n minus 2, how many sizes of n minus 2 do I have? I would have 4, right? Because, let's just see. So if we had, so we have the recurrence t of n is 2t of n minus 1 plus 1. So let's just do one of the methods to solve recurrences is just to expand the recursion a few times. So let's just say I want to plug in the result for t of n minus 1, and then just figure out what the runtime is after that. So what can I substitute in here for t of n minus 1? Well, what does t of n minus 1 look like? It's just t of n minus 1 is 2 times t of what? N minus 2 plus 1. So I can just stick that in here. N minus 2 plus 1 plus 1. I can actually just say that this is O of 1 to make it more simple. It actually doesn't matter. But if we expand this out, I have 4t of n minus 2. Well, I have a plus 2 here, and I have an O of 1. So what is the 2 and the O of 1 combined to be? Well, what is that? That's just O of 1 again, a constant time. So this is just plus O of 1. What if we did this recurrence again, but with t of n minus 3? Yeah, it actually turns out the running time is 2 to the n, right? Because each time I remove, not really remove, but I decrease the size of what I'm looking at by 1, I double the amount of recursive calls. So it's 2 times 2 times 2, n times. So that's why I get 2 to the n. All right, so solving this gives 2 to the n runtime. Cool. So I have another project idea. I think it's on the list. So we were able to get 2 to the n runtime, obviously by just thinking about how the algorithm should work, just doing this recursive call twice. It's an interesting question. Is this an optimal bound for 3 pegs, right? We may have a smaller runtime by doing a better strategy, but it might be optimal, so it'd be a good thing to look at that. What if we had more pegs? Because we only had 2 pegs to work with at a given time. What if we had more? Could we decrease the runtime there? What is the runtime then? And are there optimal bounds known? So that's a cool project idea. So any questions about Towers of Hanoi? Okay, so now for a really interesting one. So integer multiplication is something obviously computers do a lot of, right? So if we can decrease the runtime for multiplying integers, that might be pretty nice, right? So what we're given two positive n-bit numbers, so I'm just not worrying about negative numbers here or like sign patterns or anything like that. All I'm worrying about is, can I output the product? What if I had, say, an n-bit number and a really small number? I said I have two positive n-bit numbers, but this one is much smaller. What can I do? I could just prepend zeros until they're both n bits. So I really can just generalize this to say two n-bit numbers. Yeah, fewer bits. So it's like if one was 10 bits and the other was 5, I can just prepend 5 zeros on the smaller one. So they're both 10 bits, yeah. If one has fewer bits, just pad zeros. So how would you normally solve this? Again, what's the pattern in here? So brute force, then divide and conquer. So what is the brute force way to do multiplication?
Add the amount of times. If it's like 10 times 5, then you add 5 times.
So you can do addition, right? But what is the grade school multiplication with carries and all that? Right. Yeah, so you list both numbers, look at the second number, so you look at each bit in order. So let's just look at the first one. Multiply that big number by this one digit, then write that number down. Look at the second digit, do the same thing, but move everything one position. Keep going until you get to the very end of the second number, right? So what we're doing is we're looking at the first bit and the second number, then we'll output that number times the first number and add overflow bits if necessary, but that's a constant amount of extra bits. Repeat the last step, but you move everything one position over. So at the end here, I'm going to add all the intermediary numbers and possibly some overflow, but I'm just going to add all of these n-bit numbers that are shifted possibly, and then output the result. So that's the grade school multiplication that we've seen before. All right, so what's the running time here? Well, let's see. So we have these intermediary numbers, right? So how many of them are there? Well, I'm looking at each of the bits in the second number, right? And each one of those bits corresponds to an intermediary number. So that means that it's O of n of these intermediary numbers because it's n bits long for the second number because I prepended zeros, right? So there are O of n number of these intermediary numbers, right? So how long does it take to add two n-bit numbers? N-bit, I'm worrying about the bit now. Well, you have to read every single entry in the number, right? How long does it take to read n bits? O of n, right? So it takes O of n time to read and to add two n-bit numbers, and I have n of these numbers to add about. That's an n-squared algorithm, where n is the number of bits here, right? This is not the number itself. This is the bits, the number of bits in the number. So, as I've said 3 times now, can we do better? And it turns out we can. So, divide and conquer. So, this is one of the most famous papers in algorithm design by Karatsuba. And so it's called Karatsuba's algorithm for obvious reasons. So I'm assuming binary here. So this could be extended to decimal. It doesn't really matter. So we can think about a number as some number shifted over m places. So times 2 to the m, that just means shifted over m places, right? Plus some constant at the end. So you can think x0 and y0 as like the remainder when you divide by 2 to the m. Or you can also think of that as the very last digit in the number. So it's just another way of writing out the number, x and y here. All right? So x0 and y0 are the lowest order bits. So let's just look at the products, just looking at it. So x times y is just substitution for x, substitution for y, and then just do a FOIL expansion. So x1 times x1 2 to the m times y1 2 to the m is x1 y1 2 to the power 2 to the m plus, well, we have x1 2 to the m times y0, so we have that over there, plus x0 times y1 2 to the m. So we have two factors which have a 2 to the m power, and this x0, y0 at the end. So let's look at this a second. So you can think of this as x1 and x0. I actually wrote this wrong, but x1 and x0 is the number separated into two parts. So x1 is the highest order bits, like the n over 2 highest order bits, and x0 is the lowest order bits, right? So it's into two pieces. So how many multiplications do we have? Well, 2 times 2 to the m, that's just a shift. That's not a multiplication, right? So I don't need to worry about the shifts here. So the real parts of the multiplication are x1 and y1 together, x1, y0, x0, y1, and x0, y0. So how many multiplications do I have here? How many? 4, right? And what are the sizes of each of these? Well, it's the numbers, x and y, split into two pieces. How long are these numbers again? Well, n bits. Right, the whole number's n, but I split it into two parts, so n over 2 each. So basically, I have 4 sub-problems of size n over 2. So how much time does it take to combine these solutions? Well, an n over 2 bit number times an n over 2 bit number, that's order n size. How much time does it take to add 2 n-bit numbers? Order n-bit numbers? Order n, right? So the recurrence is, it's not written here, but it's 4 times t of n over 2 plus O of n, right? Because 4 subproblems, n over 2 size, and combining them takes O of n time. And if you look at the recurrence, that takes O of n squared time. So that's just the grade school algorithm all over again. So we get the same runtime. So nothing better, right? So wouldn't it be nice if I can reduce that 4 to a 3? Wouldn't that be nice? It turns out if you could reduce it to 3, you get a lower runtime. So that's what we're going to do here. All right, so here's the strategy. So we're going to do this in 3 multiplications instead of 4. So what we're going to do is, I'm going to ignore that 2 to the m stuff because it's just a shift. So I'm going to let z2 be x1, y1, z1 to be the x1, y0 plus x0, y1, and z0 to be x0, y0. So I'm just giving names to this. So the original equation is just translated to this. So instead of having the x1, y1s, I'm just basically doing the computation for z2, z1, z0, and then just plugging in. Nothing special there. But here's something silly. So let's just look at z1 again. Well, I can just, the first 2 parts of z1 are the same as what I defined it to be. But now I'm just going to add x1, y1, x0, y0, then subtract them again, right? That's silly, right? Because x1, y1 minus x1, y1, 0, and the other one's 0. So this really does nothing to the difference here. So why do you think I did this? Do you see a pattern? What do the first 4 terms look like? It looks like some kind of FOIL expansion, right? That's what it is. So if we look at the FOIL expansion, x1, y1, x1, y0, x0, y1, x0, y0. So that is just a FOIL expansion. Oh wait, how many multiplications am I doing here? x0, y0 is 1, x1, y1 is 2, Wait, am I doing 2 over there? With the x1 plus x0, y1 plus y0? How much time does it take to add 2 n over 2 bit numbers? O of n-ish time, yeah. So O of n time to add 2 bit. So I'm storing these sums, and these are order n bits each. That's just 1 multiplication. I'm not doing 2 multiplications over there. So I have 3 multiplications now, not 4. So how can I do this? I do the computation of z2, and I save it here to do this computation. Because, actually it's z0 too, z0 also. So I just do z2, z0, and then I just do these 2 sums, and then 1 more multiplication. So in total, I do 3 multiplications instead of 4. And so let's look at the runtime. So we have 3 multiplications now of size n over 2. So the recurrence is now, instead of 4 t of n over 2, it's now 3. And since all we're doing at the end is, since once we compute z2, z1, z0, then we just do those shifts, which take order n time. So it's basically factored out here. And then just do additions, which takes order n time again. So it basically doesn't do anything to the O of n here. So it still remains O of n, which is nice. So it turns out if you expand the recursion here and use the master method, you reduce this from n squared to n to the, this number actually is rounded, it's log base 3 of 2. No, log base 2 of 3, yeah. Because if you use the original grade school algorithm, it turns out that it's n to the log 4 base 2. So you reduce that 4 to a 3. So because log 4 base 2 is 2 itself, right? So here we can actually reduce it even further to 1.585. Much faster, because like we saw that n squared to n log n was a huge speed up. This one's actually even, it's not quite as dramatic, but it's actually very, very dramatic. It doesn't really work in practice very well for small integers, but it works very well for large integers. So one of the projects that I have is, can you do even better than this number? And it turns out you can, using several split methods. It's actually really cool. So, and also to see how you can actually, in practice, what kind of speed ups this algorithm and other ones would actually give you. But you can do better than this. But this is actually a really nice formulation because you can look at how many multiplications do I actually need to compute something like this. And there are actually some other algorithms. How many of you know what a matrix is? How many of you know what matrix multiplication is? So for those of you who know that, the matrix multiplication method, I'm just going to summarize it, takes n cubed time. But using a method like this for finding smaller matrix multiplications and adding those up, you can actually reduce the runtime from n cubed to like n to the 2.8 or something. So you can actually see this kind of pattern in other domains, like for matrix multiplication, integer multiplication, things like that. But the whole, right, is to be able to look at divide and conquer as a strategy for solving problems, right? So what you do is you split the problem into pieces and combine the pieces. We've seen that numerous times. But how to divide the problem up is clearly based on the individual problem, because we've seen, like for Towers of Hanoi, we only reduced the problem size by 1, but for like integer multiplication, we divided the size by 2. It really depends on the problem here, also what the base case is, but how you divide up the problem, because you may have even more pieces to split the problem up. Common divisions are equally sized pieces, and usually 2 equally sized pieces, as we've seen today. Combining solutions is where the magic happens, right? How we how much time you actually spend in combining solutions that will determine the asymptotic runtime in general, but also for the correctness, right? Because we can just recursively call ourselves, but we actually don't do anything, right? But the magic is actually how you combine the solution. Like for merge sort, you divide the list into many pieces, into two pieces multiple times, but the magic is doing the merges at the end, right? All right. So any questions on that? Okay. I'm going to start on the next topic just as a brief overview, but I'm not going to go really deep into it. But I think this is where the course actually gets really interesting, graphs. So I'd actually argue that graphs are the most important thing to know in computer science, and it really is the most important thing to know because of how many applications that these have to so many domains, as we're going to see in a second. So how many of you know what a graph is, have seen a graph? Not a plot, but like a computer science graph. So if you've, for those of you who've taken my class before on Intro to Engineering, we did these predecessor graphs for doing Lego, building Lego go-karts. And what we did was we looked at what parts are necessary to be able to build the next part. We looked at a graph. So that was just a general introduction to graphs in general, which is basically, so what they are is a two-tuple. So how many know what two-tuple means here? It's just two things given to you. That's all it really means. So what it is a set of vertices, and also called nodes, and a set of edges. So you can think of this as a bunch of points in space and lines connecting them, right? So edges connect vertices together. You also can talk about hyperedges, which have more than two vertices, but don't worry about that too much. It's just for completeness. You can have undirected or directed graphs. So by default, I call these undirected graphs. In directed graphs, suppose that I have an edge connecting vertex u to v. Well, for undirected, it doesn't matter which way we go, but for directed, it actually matters the direction. Okay. Directed edges are also called arcs, and undirected edges are just called edges. So I usually write these directed edges or arcs as ordered pairs. So here it means x has an edge going to y, and undirected is there's an edge that goes from x to y and y to x. So it doesn't matter what direction it is. So the goal of graphs in general is to be able to, first of all, look at the graph structure. Try to understand what vertices are connected to each other. For instance, what's the shortest path from this node to this other node, right? So you can think of this as like for Google Maps, right? So you can have vertices that correspond to every single city in the country, for instance, and you can have edges to be the road network of the country. So what you can look at is say the shortest path from LA to New York, for instance, using the edges in the graph. All right. So this is just a pictorial example of a really huge graph. So a bunch of vertices with a bunch of edges connecting them. All right. So many applications here. So social networks, right? So what you can model, this is actually done a lot, especially at this university, for social networks. So you model social networks as a graph and then look at the properties of the graph to answer questions about the social network. I actually did this for my undergrad thesis. So what I did was I looked at sea ice concentrations in the Arctic, and what we were able to look at was a grid, So like a square region of the Arctic, I modeled as a vertex. And what I did was I looked at the time series over time to connect vertices to each other. So if two different regions behaved very similarly over a long period of time, I made an edge between them, right? So then we can answer questions like, what is the shortest path? What is the most important vertex in this graph with respect to some metric? But here, for social networks, we can look at this as a vertex for each user and edges for two users as being friends. So like on Facebook, you can model this as an undirected edge, right? Because if you're friends, then you can see each other's profile, right? You're friends with each other. But in other cases, like if you're on Twitter, then you follow someone, but they don't necessarily have to follow you back. So in that case, it's a directed edge. Because, you can model it as a directed edge from you to the person you're following. That's actually exactly what I said. All right, so another one is solving puzzles. So how many of you know what a Rubik's Cube is? Yeah, so pretty much everyone. So Rubik's Cube is, you're given some configuration of a 3 by 3 by 3 puzzle, and then you rotate as necessary to get to the point where you have all the same color on all the 6 sides of the cube. And so you can model this as a vertex for each of the possible states, there's a ton of possible states here, and an edge between two states if there's a way to rotate the pieces such that you can get from one configuration to the other. So, and it's a huge graph, but you can answer questions about it. So what we want is, one of the huge questions is, it's actually called God's number. So if you look on Google and search God's number, you'll find one of the big breakthroughs in this. But what we want is to find out how many moves does it need to take from where I'm starting to the solve state, right? How many moves does it take? So it's basically the longest possible shortest path that I could possibly take, because I may take a really short path, but maybe there's a really long path, but it's still short in some sense. So that's called the diameter. It actually was determined, it's actually not that hard to figure out that it's 11 for a 2 by 2 by 2 grid, Rubik's Cube, but a lot of computing power was determined to find that number 20. So that no matter what configuration of a Rubik's Cube you have, each possible state can take less than 20 moves. There's no configuration that requires 21 moves, for instance. And for general, it actually was determined that it takes about n squared over log n steps asymptotically to find for any general n by n by n Rubik's Cube. So if you want to do this as a project, that'd be a great idea to look at that paper and see how they were able to prove upper and lower bounds for this. All right.
Those were the upper bounds, right? 20 is the max.
Yes.
Actually.
Yeah. There are configurations that obviously require fewer than 20 moves, like 1. But there are some that actually do require 20. There are no ways of getting 19 for some configurations. So it really is 20 here. And it's unknown for larger ones. So if you were able to solve, say, the 4 by 4 by 4, that you'd be pretty famous. So that'd be a cool project to do. But in general, there's an asymptotic bound. And it's actually tight up to constant factors for that one. All right. All right, let's just work a little more, then we can go. So just some terminology stuff. So the degree of a vertex is just the number of edges that touch the vertex. So if we go back to the really big graph, like some of the vertices on the edge only have degree 1 because they only have one edge connecting them. But some in the middle have a whole bunch of edges connecting them, right? So the degree of a vertex is just the number of edges that touch it. So incident means touching that vertex, like involve it. For directed graphs, obviously there are some edges that go out and some that come in. So we usually distinguish these by calling it the in degree, so like the number of edges that are coming into the vertex versus the out degree. So the number of edges leaving the vertex. A subgraph of a graph is just basically you take a subset of the vertices. So maybe I take these vertices and then leave out these other ones. And it should really say induced here, but the edges corresponding to those vertices that still remain, right? Because I may have left some vertices out, but I want the edges that still remain among this subset. Okay, so that's what's called a subgraph. A path, we'll be using paths a lot, is just a sequence of vertices that that are connected by an edge to the next. So yeah, so it's just a sequence of vertices that follow from the last one. And so a simple path is just one that doesn't repeat vertices. So you can have a path that goes in what is called a cycle. So you just you go out and then you come back to a vertex you've already seen, then keep going, and then you can leave or do something else. But for a simple path, you don't repeat. So yeah, that's why it's called simple. You denote a graph to be connected, which means that there's a path between every single pair of vertices, right? There's no vertex for which you can't get to any other vertex. So it's like there's not like a graph, a subgraph over here, and then like another graph over here that in which they're not connected. There's always some way to get from each vertex to every other vertex. And then some people pronounce this click, but I pronounce it clique. It's basically like a clique in general. You have say like a clique in high school is a bunch of people, a bunch of friends who are all friends with each other. It means here that it's a group of vertices which has an edge between every other vertex in that clique. So like a triangle is what is called a three clique because there are three vertices and there are three edges. So you can have 4 cliques, 5 cliques, etc. All right, I think that's a good place to stop. I don't want to burn your brains too much. So we'll talk more about graphs tomorrow.